next and final speaker is Ari Chechman, who's a principal scientist at NVIDIA. Sorry. We can do it. You want to come? Right. So he's actually a little bit research. And he's been doing work on coming up with RGB values for pixels for a very, very long time, waiting for the era of deep learning. In fact, I used a lot of these insights in my own papers. So I'm excited about his talk that is going to cast it in the light of deep learning.
Thank you very much for the introduction. And thank you very much for staying so late to this last talk of the day. I hope not to exhaust you too much, also mostly pretty pictures and videos. Okay, so this talk is going to be about some recent work I've been doing about image stylization, both neural and kind of example-based. So I'm pretty sure most of you are probably familiar with what neural stylization is. Leon Gatis introduced his seminal work a couple years ago, where you're giving usually a painting as your style example, and an image, usually a photograph, and you transfer the style onto the photograph. And people showed pretty amazing results, and there has been tons of follow-up work, and now there are very fast methods that work with any styled image, and a lot of different advancements. I'll be talking about a few of the kind of still limitations of this family of methods, neural style transfer. One of them is that many of these methods don't offer the users enough artistic control, and some people may be okay with just like a one-button algorithm, but many of the kind of more professional users want more user control. Another kind of related problem is style harmonization. So if you're pasting an object into a painting, you want to harmonize the style into the painting, and it turns out a much harder problem than kind of general full image stylization. I'll be talking about what's next beyond color and texture. I would argue that color and texture are mostly solved already with current algorithms, and what's not working so well are kind of more structured aspects of style, such as strokes, shading, different kinds of fields. I'll show how we can go to really high resolution stylization results. In our recent paper, we got results up to 160 megapixels, and some high quality video stylization results. So the first work is a pretty old one on controlling neural stylization with Leon Gatis and colleagues from University of Tübingen and Aaron Herzmann from Adobe. I'll be talking about three types of control: spatial, color, and scale control. Spatial control is something that kind of being adopted since this work by many papers. I believe the Spade paper is kind of the most recent incarnation of this idea. Basically, the idea is that you can mix and match different styles at different regions of the image based on some mask. We showed one way to do it, and since then there are many papers that show other ways to do it. You can factor style into its intensity and color values, and then given a photograph and a style image, if you apply the regular stylization method, you get a result that looks like this. And I mean, it has these kind of dark, gloomy colors of the Van Gogh Starry Night, but maybe the user wants the original kind of sunny, bright, vivid colors of his or her garden. So we proposed a couple of ways to do that. Basically, the simpler way is to transfer the style only on the grayscale channel, and then bring back the original color values. So then instead of a result like this, you can get a result that looks like this, that has the original colors of the garden, but the texture aspects of the painting. Here is another result with the Picasso style, and this is a color preservation result. The last kind of component is scale control. You can decompose the style also into its scale components. So on the fine scale, you have the brush strokes and the individual strokes. And on the coarse scale, you have these kind of bigger, coarser structures. And now the question, if you want to mix and match different styles across their different scale levels, so you want to take maybe the these round patterns as your core scales. How can you do that? So we proposed one solution. Basically, you take your input image, you transfer its colors onto the style example. You get kind of different colors of your style with the Picasso. And then you transfer only the fine aspects of this new colored style example onto the second style that has the coarse patterns by using only the fine levels. And then you get this new style example, and you transfer all the scales into the original photograph, and then you get a result that looks like this. So let's see what it's doing in the larger view. So if you use all the scales from the Picasso image while preserving the color, you get this result. But if you use at the coarse level these round patterns, you get this kind of result that has the original brush strokes of Picasso, but these kind of more rounder shapes. Here's another coarse image with different coarse structures, and another one. And this is again the whole scale result, and everything comes from Picasso. And this is the opposite. Here we take the coarse structures from Picasso and we add the fine scale details from this kind of new painting. Okay, that was about adding control. The second topic is deep painterly harmonization. This is a work with Shulman, that spoke before, as well as Fujun Wan and Kavita Bala from Cornell. So here the problem is very simple. We want to paste in a region into an existing painting and harmonize the style of the region with the rest of the painting. Sounds simple, but it's really not. So we started with kind of existing photograph-based methods, starting all the way back from Poisson blending, through some deep image harmonization methods. All of the photograph-based methods basically were not performing well. Some of them transferred well the colors, but not the texture aspect, because that's not how what they're designed to work on. We also tried some new stylization methods, starting from the original Batiste method, CNN MRF, a couple other new stylization methods, and all of them had different artifacts. They transferred better the texture, but they didn't really work well. One of the reasons was that the existing method that basically tried to pack all the style statistics into this one small region, and that's not the right thing to do. In contrast, this is our result that kind of blends better both the texture aspect and the color aspect. So the algorithm is pretty complex. Like any simple variant we tried didn't really work. So I'll just give the gist, a few kind of ingredients of the algorithm. So the first algorithm is neural style. We actually use neural stylization because it's really good at transferring textures, which is really important for paintings. But instead of transferring all the statistics from the entire painting onto the small region, we do a semantic matching such that we transfer style from only semantically relevant regions. So if you transfer a face, we want to use only the face of the painting, if it exists, etc., etc. So we were inspired by the CNN MRF work that also used kind of semantic matching. And so if you look at the original neural style method, it's a global method. So it uses the entire statistics using the gram metrics of the entire style image. And it's good in one way because it gives kind of freedom to textures to rearrange themselves, and they can kind of latch into the region they want. But as we said, it doesn't have any semantic correspondence. On the other hand, CNN-MRF is a local method, but it has other problems because it's doing the semantic match differently in different scales, which introduce kind of these typical ghosting artifacts in the eye of the monitor. So what we do is basically we mix and match the good of both methods. Our method is both local because we do this kind of semantic match, but it's also global because at each location we use a gram matrix which still allows the features to rearrange themselves and latch to the right place. And we do the search in a consistent way across scales, which again prevents the ghosting artifacts. The final component is we do the whole process in two stages, where in the first stage we roughly match the colors and textures. There are still some ghosting artifacts, and then we do this consistent match in the second stage that gets rid of the ghosting artifacts. Let's see some results. So I'll show first the output and then the input, and I'll let you guys try to guess which object was pasted in. So the first one is pretty easy. It's this starship. This is another painting by Van Gogh. Slightly harder, not if you know the painting. This is a more modern style. This is the object. This is kind of a more abstract Picasso style. We put in the clock. This style was particularly hard. Pointillism has a lot of these kind of fine structures of the painting, and basically nothing really worked in it until we found something that works. Another Picasso. Anybody wants to guess? What did you put in? Somebody who did not attend PCCV last year. Yes, the bat. We can put in also a famous president and also famous scientists in attendance. Okay, so this was still all about color and texture, and as I said before, color and texture are basically solved. So in this work that's going to be presented here actually, with my collaborators from Google, ByteDance, UC Merced, Yijun Li, Chenfang, Aaron, and Ming Xuan. We focused on pencil stylization, which is, as we found out, still a difficulty for existing methods, because it includes these kind of fine elements of texture that, of style that are really hard to capture with something like grandmasters. Okay, so pencil drawings are really a ubiquitous medium of kind of stylization. Any kid basically can grab a pencil and start drawing, and there are tons of examples of different kind of genres of pencil drawing, and different levels of abstraction, from something really coarse to something that is really fine and has all the shading and elements and fine strokes. And it's also part of a bigger kind of family of styles that are stroke-based styles, which we found that none of them really work with existing stylization methods, so there is still room for improvement, including things like ink painting and pastel painting and wood cutting, etc., etc. So, as I told you before, basically we tried several neural stylization methods, and they kind of transfer colors more or less right, but they really fail in the fine details, as you can see here on the right. And there are more methods we tried in the paper. On the other hand, there are kind of old school NPR methods that showed really beautiful results over the past, I guess, 20 years. But they're really specific for one type of style. They're not generalizable, and some of them are also harder to control. And we would like to have a fast network, and some of them are very slow, actually. A fast network that can do that. So there is one work particularly on pencil sketching that kind of worked well, and because it basically focused on image gradients and tried to preserve edges really well. But if you look closely, the results are still not really highly realistic, and they use all kinds of hacks, such as a fixed shading pattern. So this particular method will have exactly the same shading pattern for all of its results. Okay, so the challenges are basically that there are several types of kind of strokes or outlines. Some of them are more clean, some of them are more rough. And there are also several types of pencil shading, going from hatching to blending, cross shading, stippling. So there's a really big variety. In addition to that, there is no really an aligned data set that exists, or a paired data set. So we had to basically come up with one. So the kind of the naive baseline is a cyclogen that was mentioned several times today. That is basically an unaligned style transfer or image translation method. And it does a decent job, but if you can look carefully, you can still see kind of quite a few artifacts, and the details are not really high. Our approach is basically to separate the problem into its outlines and shading aspect, and we have two networks, one that generates the outlines and one that generates the shading. And we basically create a paired data set. And then we can translate several different types of style into one, using one model, using our one hot vector result. So how do we create a paired data set? We take existing, for the outlines, for example, we take existing pencil drawings, and we abstract them using an edge detector. In this case, we chose the X-Dog because it has a nice property that the edges look kind of similar between drawings and real images. Remember that in the end we want to take a real image and stylize it, but our training is based on drawings. So this is the way we create the paired data. This is an illustration why we chose X-Dog on the right, because it's, as I said, consistent between images and drawings. And then we train the network with 30 such images using kind of patches. We cropped from both images in a consistent place, and we have one hot vector to choose between rough or clean sketches. For the shading branch, we use actually two inputs. One is the tone and one is the edge map. And we use guided filtering to get the tone and some edge detection to get the edges. And again, the training is done very similarly with, again, a one hot vector that can choose different types of shading. Some results of just the outline branch. So you start with some kind of clean vector illustration, and you can get these kind of pencil drawings, or these for this example in a video. We have some control over, in addition to the one hot vector, over the width of the X-Dog, so that gives kind of another level of control that, again, professional artists will really appreciate. For the shading branch, again, we can produce different results with different types of shading, stippling and hatching. In this result, we mixed one type of outlines, the clean outlines, with the stippling shading, and added back the original colors like we did in the previous one. And here is a frame-by-frame stylized video result that use different types of outlines, rough outlines, and different hatching than before, and again brings back the colors. Okay, that was about pencil drawing. The results are kind of better than state of the art, but there is still room for improvement, so I kind of call you guys to continue and work in this area. Now to a arguably very simple trick that can enhance any neurostylization technique and improve its resolution. This is a paper that was just presented at Expressive with Mike and Cynthia from Adobe and colleagues from CPU in Prague on improving and enhancing neurostylization. So basically there are kind of two paradigms for stylization. One is the patch-based or example-based approach, which is the good old image analogy that was brought up in this workshop already. Where what they did, what Aaron Hertzman and colleagues did in image analogies, they extracted basically the grayscale map as the guiding channel from the painting and from the input image, and used the grayscale as the guide to transfer the style. So it's basically transferring the style based on the intensity. Which is great because, on one hand, because the texture quality you can get with this method is really high, and you can get very high resolutions, but it has wrong semantics because it's using grayscale as your guide. On the other hand, the neural stylization methods don't have any guiding channels. The guidance is kind of done inside the network, but they handle textures really well. The results are kind of low to medium resolution in terms of what, for example, Photoshop users would like to have. And they have good semantics. So kind of the vegetation goes to where vegetation should go, the red side of the building goes to the red side of the building, etc. So the idea is basically to take these results of neurostylization and use them as a guide instead of a grayscale channel. And we basically downsample and blur the original painting to use as the other guided channel, and then you can get a result that looks like this, that has the original kind of semantics of the neurostylization, but much higher resolution and quality of strokes. Let's see some results. Well, this is more details about the algorithm works, how it works, but it's not really that interesting. Some results, so you can take any of your favorite neurostylization result, like Guetao from last year, for example, and then apply our enhancement and get basically a better result that preserves better the fine details. Here is a few results with different methods. This is the original Gattis et al. And our enhancement. This is, by the way, a 5,000 by 4,000 image. This is a different stylization method, and our result. Basically, our method kind of projects the result onto the original colors and textures of the painting. It doesn't let the algorithm to go too wild. That's it for enhancement. Very simple trick. You can download the code, play with it, enhance any of your favorite method. I think it's really useful. Last topic, video stylization. This is going to be presented at SIGGRAPH this year with the same collaborators as before. Why is video stylization important? Basically, or why is it hard? If you look at the Lavin Vincent movie, for example, a full-length movie that was released 2 years ago, it took more than 6 years, 125 artists to paint this movie by hand. It's a really tedious task. So how can we help basically the artists with this task? So our framework is kind of very simple. We show a video to the user. The user chooses a keyframe, paints manually with existing techniques, or maybe with neural stylization, or however you want, one keyframe. And then we transfer the style to the rest of the video, usually a short kind of clip around that frame. Now you may think, there are plenty of video stylization methods out there. Some of them were shown before. We tried all of them. I mean, you can look at the video SIGGRAPH submission. None of them really works. Some of them have kind of spatial issues. The textures are just not what the artist wanted. And some have temporal issues, so we tried some temporal stabilization techniques, including my paper from last TCCV with some colleagues. Nothing really works. Okay, so what? Yeah, here's another method that did not work. Okay, what the method is based is on a good old patch-based stylization or example-based stylization, and the most close kind of work to ours is our own kind of SIGGRAPH paper from a couple of years ago on face stylization. Here are some results of that paper. And the way that works, I'm sure many of you know, again, good old page-based stylization. You want the target to look locally, like someplace in the source. And to achieve this, you write down this kind of equation that is working on patches, solve it in a multi-scale fashion, and get, for example, a texture, as we can see on the right. Or in the case of image analogies, you have another guiding channel that tells you where patches should go from the style to the target. That helps to kind of rearrange the patches, and then you get a result that looks on the right. Again, very simple. In the case of faces, we use the kind of face-related guiding channels, including a face segmentation that we blurred a little bit to give the patches a little bit more freedom. We use a face tracker with which we kind of worked the guiding flow field in a smooth way around the features that we track. And we use histogram equalized gray channels. And that's how we got the results that we showed before. Here we have kind of a general scenario. It's not necessarily a face. Usually it's not. It's usually a subject or an animal or some object. So we use different guiding channels. One of them is the previous frame, basically, as vectored with the flow. One is the mask of the subject. We assume we know where is the subject, which is a common thing in production. The correspondence field, as before, which basically tells roughly the patches where they should go. They shouldn't move too much. And that avoids things like something that was on the left side to go to the right side and stuff like that. And an edge map. And we show in the paper why each of these terms is important. I'll just show you some final results. So here is a kind of a longer sequence where the user starts with one keyframe, and then you propagate the style onto the entire shot. At some point, the result starts to deteriorate. You start to get kind of artifacts, especially when the subject kind of moves a lot or the pose changes. At that point, the user decides, okay, I need to change and fix the loop, and we produce another keyframe, and then another one, and another one. In this case, we had 8 for this sequence. Here are a few more results.
Get in my car.
More well-known videos. Note that some of these videos don't have actually a temporally coherent style, which is a good thing. Like as long as the flickering is controlled, artists actually
bingo!
want that effect. They want the individual strokes to move. Yeah, you can see another example here. And in our method, it indeed kind of preserves this property of kind of controlled flickering.
Please, you don't understand. Nothing in there is dangerous.
Yeah, that's it. So recent advances in neural and patch-based stylization. Thank you very much for listening. We have time for a couple of questions. People are tired. Okay. But then let's back to speaker again.